In this lecture, we will discuss what is meant by the partition function. So, consider a system specified by the macro state, total number of particles n and total volume v and equilibrium temperature T. Okay, so a system specified by this macro state is termed as the system in canonical ensemble because here temperature is fixed. In micro canonical ensemble, we will have a fixed energy. And we already discussed about canonical ensemble and we obtained an expression for Helmholtz free energy which is A equal to minus kT log sigma r e raised to minus beta er. Okay? This summation goes over all the microstates of the system. Now we will define a quantity Qn of Vt. So it will depend on N, V and T. Qn of Vt is equal to sum over all the microstates e raised to minus beta er. E raised to minus beta er. This quantity is called partition function. This quantity is called partition function. Now, in German, Substanzsumme. This word means sum over states. And sometimes this partition function is represented by the letter Z. But in Pathria, textbook by Pathria, the partition function is denoted as Q. So we will also follow the same notation in this series. Now, probability of finding a system in a particular energy value ER is given by PR is equal to E raised to minus beta ER divided by sigma R E raised to minus beta ER. This I can write in terms of partition function as E raised to minus beta ER divided by Qn of Vt. We all know that the system should be in any one of the state specified by any of the energy eigenvalue. Okay, it should be found in a particular microstate. So the total probability should be 1. If you sum over all the states, the total probability should be 1. That means if you take the sum of this quantity, sigma e raised to minus beta er divided by qn vt, that will be numerator is again qn. So qn vt divided by qn vt, you will get 1. Okay. So we can say that this qn is actually a normalization constant, which makes the probability, total probability as 1. Or we can say that Qn encodes how the probabilities are partitioned among different microstates depending on their energy values. Okay? Depending on their energy values, this partition function says us how the probabilities are partitioned among different microstates. Okay, that is why it is known as partition function. You will get more idea about partition function as we proceed further. Okay. Now, QNBT, its dependence on T is clear from the expression itself because it contains e raised to minus er by kt. So there is T explicitly. So that dependence on T is clear. Now the dependence on N and V, that will come through the energy eigenvalues. Okay. So for explaining that, you consider a particle in a one-dimensional box as your system. Then the energy eigenvalues are n square h square divided by 8ml square. This is 8ml square. Now, L square you can write it as V raised to 2 by 3 where V is the volume. So, energy eigenvalues for a particle in a one-dimensional box depends on the volume. Okay. So, that means if energy eigenvalues depends on volume, then naturally the partition function will also depends on volume. Now consider another example which will explain you what is the dependence on n. Consider a one-dimensional harmonic oscillator. one-dimensional harmonic oscillator. Its energy eigenvalues are E equal to n plus half h cut omega. N can take value 0, 1, 2, etc. So the first energy value E1 is half h cut omega. Second energy value E2 is 3 by 2 h cut omega, and so on. Now consider two one-dimensional harmonic oscillators of same frequency. That is, your system consists of two oscillators, okay, two particles or two oscillators of same frequency. Then the total energy of the system will be the sum of the individual energies of the oscillators, because we are assuming that the oscillators are non-interacting. Then N1 plus half h cut omega will give you the energy of first oscillator. N2 plus half h cut omega will give you the energy of second oscillator. Both N1 and N2 can take values 0, 1, 2, etc. Then what are the possible energy eigenvalues for the system? If N1 and N2 both are 0, then you will get half h cut omega plus half h cut omega, that is h cut omega. This is the lowest energy possible for this system, which consists of two one-dimensional oscillators. Now, the second possible energy is N1 can have 1 and N2 can have a value 0. Then you will get 3 by 2 h cut omega plus half h cut omega, that is 2 h cut omega. Similarly, N1 can be 0, N2 can be 1. That will also give you a 2 h cut omega. Then N1 can be 1, N2 can be 1. That will give you 3 h cut omega, and so on. So, these are the possible energy eigenvalues if the system consists of two one-dimensional harmonic oscillators. So, as the number increases, the energy eigenvalues will change. The energy eigenvalues will change. So E depends on N. So that is why this partition function will also depends on N. So the dependence of partition function on V and N comes through the energy eigenvalue. Okay. Now, partition function may also depend on other parameters like, say, the strength of electric field or strength of magnetic field, etc. because they can alter the energy eigenvalues. Anything which can alter the energy eigenvalues can come in the argument of this partition function. Okay. So, it can depend on strength of electric field or strength of magnetic field, etc. And then this Qn can be written as V, T, E, B, etc. Okay, so that is the dependence of a partition function on different quantities. Now we have Helmholtz free energy. Here I represented it as A of nVt is equal to minus kT log Qn of Vt. This we derived in the last lecture, and we discussed in the starting of this lecture also this relation. A is equal to minus kT log Q. A is an extensive quantity. It is Helmholtz free energy, and as the size of the system increases, it will also increase. A is an extensive quantity, T is an intensive quantity, so log Q should also be extensive. Log Q should also be extensive. Okay, that I will explain later. So keep this in mind. Log Q should be an extensive quantity. Now, we have Helmholtz free energy A is equal to U minus Ts, where U is the average energy of the system. S is entropy. dA is equal to du minus Tds minus SdT. From first law of thermodynamics, du is Tds minus Pdv plus mu dn. Then this minus Tds and minus SdT. Tds will cancel with this minus Tds. Then you will get dA as minus SdT minus Pdv plus mu dn. Now you can take three partial derivatives of A, one with respect to T, that will give you minus S, or you can write it as S equal to minus dou A by dou T, then keep V and N constant. Okay. So at a constant volume and number of particles, uh, negative derivative of negative partial derivative of A with respect to temperature is entropy. In a similar manner, if you take a partial derivative with respect to volume, keeping T and N constant, you will get a pressure. And if you take a partial derivative with respect to N, keeping T and V fixed, you will get chemical potential mu. So once we have the value of Helmholtz free energy of a system, by taking partial derivatives with respect to T, V and N, you can find the values of entropy, pressure and chemical potential for a system in canonical ensemble. Now, what is CV? Specific heat at a constant volume. That is nothing but dou U by dou T at a constant number of particles and constant volume. And the U is nothing but A plus Ts, because we here mentioned that A is U minus Ts. So U is A plus Ts. Taking derivative, this becomes dou A by dou T at a constant N and V plus T into dou S by dou T at a constant N and V plus S into dou T by dou T is 1. Okay. So this Ts you apply product rule. So you will get 3 times. But we already know that S is minus dou A by dou T at a constant N and V. If you substitute for this last S, then the last term and first term will cancel. And in the second term, that becomes a second derivative. Okay, this S is minus dou A by dou T. So this term becomes minus dou square A by dou T square at a constant N and V. This is specific heat at a constant volume. Now, Gibbs free energy G is A plus PV. Again, substitute for P from this relation minus dou A by dou V at a constant T and N. So substitute here. That will give you G is equal to A minus V into dou A by dou V at a constant N and T. But A is an extensive quantity. So I can write A of NVT as some function which is independent of the size into the number of particles of the system. So as the size of the system increases, this n will increase, keeping this f a fixed quantity. So that will make A extensive. Okay. So A extensive means you can write it in a form like n into f of Vt. What is this V? Small v. Small v is capital V, volume divided by total number of particles. So small v is an intensive quantity, T is an intensive quantity, so F is also intensive quantity. And if you multiply with n, then this A becomes an extensive quantity, because any change in size will reflect in the value of n. Now take the derivative of this A with respect to n, dou A by dou n at a constant V and T. When you take the derivative with respect to n, you take f and take the derivative of n, that will give you the first term, plus take n and take the derivative of f, that is the second term. Okay, product rule, dou f by dou n at Vt. This is f plus n into, what is dou f by dou n? Dou f by dou n is, I can write it as dou f by dou v into dou v by dou n, because f is a function of v. We are going to take the derivative with respect to n. You can apply chain rule. So dou f by dou v into dou v by dou n. What is dou v by dou n? From here, dou v by dou n is minus v by n square. Minus v by n square. So substitute here. One n will cancel. You will get. Now to multiply with this n. N into dou a by dou n Vt is equal to n into f. N into f. And there is already an n. You multiply with the n, this will be n square, that will cancel this n square, so it is simply minus v into dou f by dou. Now I will take the partial derivative of a with respect to v, dou a by dou v at a constant n and t, that is equal to, at a constant n, that means if you keep f as fixed and take the derivative of n, that will give you 0. Then keep n as fixed, take the derivative of f. So n into dou f by, actual derivative is with respect to capital V, but this function is, f is a function of small v. So again apply chain rule, dou f by dou v into dou v by dou. So dou v by dou v, what is dou v by dou v? It is 1 by n from this expression. So that n will cancel with this, you will get dou f by dou v. Now multiply this with a v. V into dou a by dou v at a constant n and t. that will give you V into dou F by dou V. Okay, this is dou F by dou V, multiply with the V. Now add these two expressions. N dou A by dou T, so if you call this as A, and if you call this as not that, this as B. Okay, A plus B will give you, A plus B will give you n into dou A by dou n at a constant B and T plus V into dou A by dou V at a constant n and T is equal to this negative term and this positive term cancels. You will get NF. What is NF? NF is actually A. So that will give you an important identity. N into dou A by dou n Vt. N into dou A by dou n Vt is nothing but A minus V dou A by dou V. So here you have an A minus V dou A by dou V that you can replace with N into dou A by dou A. N into dou A by dou A. Okay, and this is dou A by dou n at a constant V and T. We wrote that expression dou A by dou n at a constant T and V is mu. So you will get G is equal to mu n. So Gibbs free energy is actually chemical potential into number of particles in the system. G is equal to mu n. This is a very famous relation. So that you can obtain from here by using this concept. Okay, using the concept of A is an extensive quantity, you can arrive at the relation for G as mu into N. Now, T is minus dou A by dou V at a constant N and T. So, that is equal to minus dou by dou V of A is minus KT log sigma e raised to minus beta ER. This minus and this minus becomes plus, KT will come outside. Dou by dou V of logarithm of a quantity. So that will give 1 by sigma e raised to minus beta ER because log x derivative is 1 by x into function of a function sigma e raised to minus ER by KT. But this ER will have dependence on V. So 1 by KT into minus dou ER by dou V. Okay, ER has dependence on V. KT and KT will cancel. So this will give you minus sigma dou ER by dou V. Dou ER by dou V into e raised to minus ER by KT divided by sigma R e raised to minus ER by KT. If you take a PdV, that is multiply with this PdV, then this dV will cancel and you will get it as minus sigma e raised to minus ER by KT DER divided by sigma R e raised to minus ER by KT. But this e raised to minus ER by KT divided by sum over all microstates e raised to minus ER by KT is nothing but probability PR. So that will give me minus sigma R PR DER minus sigma R PR DER. Okay. So the left hand side is PdV, right hand side is sigma R PR DER. That is nothing but the average energy. Average energy. Why? Because if you have a quantity like energy and the probability of finding the system in that energy level, then average energy is sigma R ERPR. If you want to find the average number of particles, then that will be sigma R NRPR. Okay, so average of any quantity in the system, you can find it by the equation average of any quantity, say x bar, you can write it as sigma xi pi. Okay, this is the definition. If you have probability of a particular value xi, then sum or all the possible values multiplied with this probability, then you will get the average value of that quantity. Because each of these x's have different probability. If all have the same probability, then average will be the sum divided by total number. But each of these quantities will have different probability. Then the average of the quantity is sigma equal to 1 to n xi pi. Similarly, if ER is the energy eigenvalues, then average energy of the system is sigma R ERPR. Suppose PR is kept fixed, then if you take DU, that will give me sigma R PR DER. PRDE. Okay, so this du, here I write it as du instead of PRDER, I write it as minus du. This du is actually the change in energy of the system during a process that alters energy levels keeping PR fixed. If you fix PR probabilities and vary the energy levels, that will make a change in average energy of the system, and that is given by minus du. This minus du is actually change in energy of the system during a process that alters only energy levels, keeping PR fixed. And that can be, the left hand side says that that can be visualized by a process in which there is a change in volume. In which there is a change in volume. Okay. So if you have a process which makes a volume change for the system, then that will give you a change in energy levels, keeping the probabilities fixed. Okay, keeping the probabilities fixed. And we can also say that if you make a change in volume dv, then p is nothing but the force accompanying that process. For this to happen, there should be some force, and p represents that force. So p, actually we introduced it as purely thermodynamic quantity. Now it has a mechanical meaning as well. Now I will make this point more clearer. You have the average energy of a system, or average internal energy of a system, which is U is equal to sigma R ER PR. We can alter this internal energy of a system in two different ways. One is by altering the energy eigenvalues, the other one is by altering the probabilities. But in plus 2 classes, we studied that we can increase, or we can change the internal energy of a system either by adding heat to the system or by doing work on the system. So now we will explain those things. You consider this plot. These lines, the length of these lines represents the probability values. Suppose the this y-axis has energy values. Suppose you have a system having three energy values E1, E2, E3, in which E3 is greater than E2, which is greater than E1. The probability of finding the system in these energy levels are shown here. For the energy E1, probability is say 0.5, 5 squares, it is 0.5. For finding in energy E2, it is a 0.3, and for finding in energy E3, it is zero point 0.2. So total probability is 1. But as energy increases, the probability decreases. Why? Because we already knew the expression PR is e raised to minus beta ER by Q. So as energy increases, there is an exponential decrease for probability values. So as energy increases, the probability will decrease, and uh, the total probability should be always 1. Now, if you add heat to a system, what will happen? The energy eigenvalues will remain fixed at these values itself, but the probability will get altered. The probability of lowest level, it is reduced to 0.4, and the second level the probability increased to 0.35. For third level also it is increased. Okay, so total probability again it will be 1. But as you give heat to the system, the temperature will increase, and there is more probability of finding the system in higher energy levels. Okay, the probability of finding the system in higher energy levels will increase. Now, the second case is you have again the same probability and same energy levels. Now you are doing mechanical work, okay, on the system. Now that will alter the energy levels. If you are doing work means that will change the volume. If it is a mechanical work, that will change the volume, and that will alter the energy levels. So the position of energy levels are different, but the probability remains the same. There is no change in probability. So adding heat to a system means change in probability without any changing energy level. adding work or doing work on the system means a change in energy levels keeping the probabilities fixed. Okay, that is the case. We can also apply a magnetic field or electric field to a system in order to alter the energy levels. That is also possible uh, to make a change in internal energy of the system. Now we will calculate entropy of a system in canonical ensemble. We have probability PR is equal to e raised to minus beta ER divided by sigma e raised to minus beta ER, and sigma e raised to minus beta ER is nothing but partition function Q. You take logarithm on both sides. So log PR is equal to minus beta ER minus log Q. Okay. What is the average value of this logarithm of probability? That is equal to minus beta into average value of ER minus log Q. Log Q is a fixed quantity for a system. So the average is that value itself. Okay. Now average value of log PR is equal to minus beta into what is average value of ER? That is nothing but average energy U minus log Q. So average value of log PR is equal to minus beta into what is U? U, we already know that an expression in terms of Helmholtz free energy, A plus Ts, and we have A is minus Kt log Q. So minus log Q is nothing but A by Kt, that is beta A. 1 by Kt is beta. This minus beta A and this plus beta A will cancel. So you will get it as minus beta into T into S. Beta is 1 by Kt, that T will cancel. So it is minus S by K. Minus S by K. So S is equal to minus K into average value of log PR. Minus K into average value of log PR. Average value of log PR is sigma R PR into log PR. We already mentioned that average value of any quantity is sigma R XR PR. Okay. So average value of log PR is sigma R PR into log PR. So this is the equation for entropy of a system in canonical ensemble. S is equal to minus K into sigma R PR log PR, where PR is the probability of finding the system in an energy eigenvalue ER, in a microstate specified by an energy eigenvalue ER. So entropy is solely determined by the probability values PR. So K is a constant. So entropy is solely determined by the probability values PR. Now we will consider different cases. The first case is when the system is in ground state, and that happens when the temperature is 0 Kelvin. If the ground state is unique, then we can say that the probability PR is 1 for R equal to 0 state, and for all other states PR will be 0. So when you calculate entropy, for R is equal to 0, this PR is 1, so log 1 will be 0. For all other R values, this PR itself is 0. So entropy is 0. Some or all states you will get it as 0. So if you have only one ground state, then the system will be obviously in that state, and that means a 0 entropy and a maximum order for the system. Okay, disorder of the system is 0. Now this entropy is 0 at absolute 0 is the statement of third law of thermodynamics. Okay, Nernst heat theorem or third law of thermodynamics says that entropy is 0 at absolute 0. But if we have degenerate ground state, suppose there are omega 0 number of states in the ground state. Okay, in the ground state energy, there are omega 0 different microstates. That is the meaning of degenerate ground state. Then probability of finding the system in any one of the microstate PR will be 1 by omega 0. In the same energy, all microstates have the same probability, equal a priori probability. Microcanonical ensemble നമ്മൾ discuss ചെയ്തതാണ്. In microcanonical ensemble, the system is having a constant energy. So if we consider the ground state, that is fixed energy, and there are different microstates possible for that energy state. That is the meaning of degeneracy. Then PR is nothing but 1 by omega 0. If you substitute PR as 1 by omega 0, you will get S is equal to K log omega 0. How? This PR is 1 by omega 0. This PR is also 1 by omega 0. Summation is over all the microstates. That is, R will run from 1 to omega 0. Log 1 by omega 0, you can write it as minus log omega 0. This minus and this minus becomes plus. So that will give you K into sigma R equal to 1 to omega 0, 1 by omega 0 log omega 0. So you write the term 1 by omega 0 log omega 0 plus 1 by omega 0 log omega 0 plus 1 by omega 0 log omega 0 like omega 0 times. Okay, that will give you K log omega 0. K log omega 0. Sum over all the states, you will get K log omega 0. So entropy will be K log omega 0 if there is a degeneracy in the ground state. If there is a unique ground state, then this omega 0 will be 1 and entropy will be 0. Now, second case, as temperature increases, number of accessible states also increases. Okay. From T equal to 0, if you increase the temperature, the number of accessible states will increase. More PRs becomes non-zero. In the earlier case, PR is equal to 1 for R equal to 0. All other PRs are 0. As temperature increases, more PRs becomes non-zero. And since sigma PR equal to 1, sigma PR is equal to 1, value of each PRs becomes exceedingly small. Okay, PRകൾ കൂടുതൽ നോൺ സീറോ ആവുന്നതിനനുസരിച്ച് ടോട്ടൽ വാല്യൂ 1 കീപ്പ് ചെയ്യണം എന്ന് പറഞ്ഞാൽ each of the PR value will be very small. In the case with the T equal to 0 Kelvin, there is only one PR. That value is 1. All other PR values are 0. But if more and more PRs are non-zero, that means the individual PR value will be very small because the total sum is always 1. Okay, അപ്പോൾ ഓരോ PR വാല്യൂ ചെറുതായി വരും. കൂടുതൽ PR non-zero ആവുന്നതിനനുസരിച്ച്. എണ്ണം കൂടുമ്പോൾ ഓരോന്നിന്റെ ഇൻഡിവിജ്വൽ വാല്യൂ കുറഞ്ഞു വരും to keep the sum constant. S is equal to minus K sigma R PR log PR. When PR value is very small, log PR becomes very large negative value. Okay, because log 1 is 0, and if you reduce the value from 1, then log becomes negative, and as the value decreases, that becomes a very large negative value. So since PR is exceedingly small, this log PR is exceedingly large negative value, and this negative will make that entropy a very large positive. So as temperature increases, entropy will increase. So largeness of entropy, that is a measure of high degree of statistical disorder. Probability ഓരോ സ്റ്റേറ്റിലുള്ള കൂടുതൽ സ്റ്റേറ്റിൽ കാണാനുള്ള പ്രോബബിലിറ്റി കൂടുന്നു എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ that means high degree of statistical disorder. കാരണം ഓരോ സ്റ്റേറ്റിലും കാണാനുള്ള പ്രോബബിലിറ്റി കുറഞ്ഞു പോകും. കൂടുതൽ സ്റ്റേറ്റ് അവൈലബിൾ ആവുന്നു, ഓരോ ഇൻഡിവിജ്വൽ സ്റ്റേറ്റിലും കാണാനുള്ള സാധ്യത കുറയുക എന്ന് പറഞ്ഞാൽ that means a greater disorder. Okay, so largeness of entropy is high degree of statistical disorder. Now I will discuss 3 simple examples. Let there be 2 states possible for the system. Then suppose that they occupied with the equal probabilities. P1 is equal to half, P2 is equal to half. What is entropy? It is minus K half log half plus half log half, because sum over all the microstates, the probability into log probability. That's entropy on our equation. So minus K half log half plus half log half, that will give you minus K into half log half is minus 0.346 minus 0.346. You will get it as 0.693 K. K is Boltzmann constant. If there are 3 states possible for the system with the probabilities, equal probabilities 1 by 3, 1 by 3, 1 by 3, then S is minus K 1 by 3 log 1 by 3 3 times. So that will give me K log 3, and it is 1.098 into K. So entropy increased. Okay. Here the number of states increased, probability of each state decreased, so entropy in effect increases. Let there be 100 states, all have the same probability, then each one will have a probability of 1 by 100. Then entropy S is minus k into 100 times 1 by 100 log 1 by 100. That will give you k log 100, and that is 4.605k. So entropy again increased. So as the number of states increases, probability of each state will decrease and entropy will increase. Okay, so increase in entropy is a measure of statistical disorder. Okay, I think now it is clear. Okay, the third case, we can use S is equal to minus K sigma PR log PR for microcanonical ensembles. What is the case with the microcanonical ensemble? In a microcanonical ensemble, energy is fixed, okay, it is having a fixed value, and there are omega states, all are equally likely to occur. In that particular energy, there are omega number of microstates, all are equally likely to occur. So PR is 1 by omega. The individual probability is 1 by omega. If you calculate the sum, you will get it as minus k sigma r equal to 1 to omega, 1 by omega log 1 by omega. Okay, 1 by omega log 1 by omega, you add it omega times. Then what will happen? You add it omega times. That means omega into 1 by omega log 1 by omega. This omega and omega will cancel. That will give you log 1 by omega, that is minus log omega, and this minus k and this minus log omega will give you k log omega. This is the famous relation we derived in the earlier classes for microcanonical ensemble. S is equal to k log omega. K log omega. Okay. For canonical ensemble, S is equal to minus k sigma PR log PR. Okay. The fourth case is degenerate energy levels. Degenerate energy levels. In most physical cases, the accessible energy levels to a system are degenerate. That means there are more than one level having the same energy. Suppose there are GI states having same energy EI. There are GI states having same energy EI. Then partition function Qn of Vt is equal to sigma I GI e raised to minus beta EI. Okay, you have to multiply with the number of states in that particular energy level EI. Then probability of finding the system in that particular energy level is Pi is equal to Gi into e raised to minus beta Ei divided by sigma I Gi e raised to minus beta. If you have only one level corresponding to a particular energy value, then PR is e raised to minus beta ER divided by sigma e raised to minus beta ER. If you have GR levels corresponding to an energy value ER. Okay. That means G1 levels corresponding to energy value E1, G2 levels corresponding to energy value E2, and so on. Then the probability of finding the system in an energy value EI will be GI. This is a weight function or weight factor. Gi into e raised to minus beta ei divided by sigma I Gi e raised to minus beta I. That is, if there are more levels corresponding to a particular energy value, probability will also be high. Okay, if there are more levels corresponding to a particular energy value, probability of finding the system in that energy value will be high. So probability will depend on two factors. One is degeneracy of the level, degeneracy of the level. Second one is the Boltzmann factor e raised to minus beta. Okay. So if the system has a degeneracy, then probability will directly proportional to degeneracy. As degeneracy of the level increases, the probability of finding the system in that energy level will also increase, and it will also proportional to the Boltzmann factor e raised to minus beta. Now we will consider two limiting cases. Temperature tends to 0. Temperature tends to 0. T tends to 0. Okay, this we already discussed. And Q partition function is nothing but sigma I G. Q is sigma I gi e raised to minus ei by kt. In the limit t tends to 0, you have g0 e raised to minus e0 by kt plus g1 e raised to minus e1 by kt plus etc. But e0 is 0. So in the limit t tends to 0, this e raised to 0 becomes 1. So that will give me a g0. All other terms in the limit t tends to 0, this exponential term, since e1, e2, etc. are non-zeros, this becomes 0 raised to minus infinity. All other terms become 0 raised to minus infinity, and that becomes 0. So you will get q as g0. Okay, so in the limit t tends to 0, we can say that partition function is degeneracy of ground state. In the limit t tends to 0, partition function is nothing but degeneracy of ground state. In the limit t tends to infinity, what is the meaning of partition function? In the limit t tends to infinity, what happens? G0 e raised to minus e0 by kt plus g1 e raised to minus e1 by kt plus etc. So in the limit t tends to infinity, this each of these terms becomes e raised to 0, e raised to 0. E raised to 0 is 1, so you'll get q is equal to g0 plus g1 plus g2 plus etc. That is the total number of microstates. Total number of microstates. So in the limit t tends to infinity, partition function represents total number of microstates. In the limit t tends to 0, partition function represents the degeneracy of ground state, the number of levels in the ground state. Okay. Now the case with the continuous energy levels. Continuous energy levels. Usually, the number of particles n and volume of the system V will be very large. Okay, we consider in thermodynamic systems, the number of particles and volume is usually very large. So the energy levels depends on n and v. We already seen that for a particle in one-dimensional box, energy eigenvalues is n square h square divided by 8m v raised to 2 by 3. So as v increases, this energy values will decrease. So the spacing between the adjacent energy values will be very small. The spacing between adjacent energy values will be very small. That is between an energy E and a very close energy E plus DE. Okay, E യോട് വളരെ അടുത്തുള്ള ഒരു എനർജി നമുക്ക് പറയാം. Between E and E plus DE, there will be large number of energy levels because spacing between each energy level is very small. If you consider a small energy interval DE, in that energy interval itself, there will be a large number of levels. So we can treat E as a continuous variable instead of a discrete one. You can treat it as a continuous variable, and you can define P of EDE as probability of system having its energy in the range E and E plus D. Okay, P of EDE will represent the probability of system being in an energy which lies between E and E plus D. സിസ്റ്റത്തിന് ഇക്കും ഇ പ്ലസ് ഡി എന്നുള്ള എനർജിക്കും ഇടയ്ക്ക് കാണാനുള്ള പ്രോബബിലിറ്റി ആണ് പി ഓഫ് ഇ ഡി. And P of E d is proportional to G of E dE to e raised to minus beta e. E raised to minus beta e is Boltzmann factor. G of E dE is the number of energy levels whose energy lies between E and E plus D. G of E is density of energy states around energy value E. That means G of E is the number of energy states per unit energy width. Okay, that is in an energy width dE, total number of states will be G of E dE. G of E dE. Now the normalization, that is, we know that the total probability should be 1. So here instead of summation you have to integrate over all the energy values, and from this we can calculate the proportionality constant as 1 divided by integral 0 to infinity e raised to minus beta e G of E dE. Therefore P of E dE is equal to e raised to minus beta e G of E dE divided by integral 0 to infinity e raised to minus beta e G of E dE. This is the probability of finding the system in an energy value which lies between E and E plus dE. And here we can define the partition function as Q Qn of Vt is equal to 0 to integral 0 to infinity e raised to minus beta e g of e d. Okay. Instead of summation, you have integration. This is the partition function for a system having continuous energy. Continuous energy. Now, the expectation value of f, that is, or mean value of f is sigma I pi. This is the case with the discrete system, and for continuous case that will change to, this is a pi. You can write it as e raised to minus beta ei divided by sigma e raised to minus beta ei. In the case of discrete energy levels. Now, for continuous energy level, this summation will get replaced with integral and with the density of states. So 0 to infinity f e raised to minus beta e g of e dE divided by integral 0 to infinity e raised to minus beta e g of e dE. That will give you the expectation value of f, or the mean value of f. Now, relation between density of states and partition function. Okay, we already have this relation. Partition function q is integral 0 to infinity e raised to minus beta e g of e dE. G of e dE. From the classes of mathematical physics, we know that Laplace transform of a function f of t, Laplace transform of a function f of t is defined as f of s, this is capital F and this is small f. F of s is equal to integral 0 to infinity e raised to minus st f of t dt. This is an integral transform. This is a definite integral over the variable t. Then you will get a function of s, and that is given by capital F of s. This is the definition of Laplace transform. So this equation for partition function is similar to this one. Similar to this one. Instead of t, you have e here. Instead of s, you have beta. Okay, so we can say that partition function is Laplace transform of density of states. Partition function is Laplace transform of density of states. Okay, here you have a condition s greater than 0 for convergence. So in this case, beta is greater than 0. We already know that beta is 1 by kt, and that is a positive. So we can safely say that this q is Laplace transform of density of states. So density of states g of e is inverse Laplace transform of partition function q of beta. Okay. So density of states is inverse Laplace transform of partition. Inverse transform can be calculated using Bromwich integral, and if f of s is the Laplace transform of a function f of t, then we can calculate f of t once f of s is given using this integral, and it is equal to 1 by 2 pi I integral gamma minus I infinity to gamma plus I infinity e raised to st f of s ds. So instead of e raised to minus st in Laplace transform, here we have e raised to st, and the integral is from gamma minus I infinity to gamma plus I infinity. Here gamma is the real part of s. Assuming that s is complex, it is some gamma plus I beta. Then gamma is the real part of that s, and this is the equation from Bromwich integral. And for more details, you can refer Afghan Mathematical Methods in Physics by Afghan. Now, applying this integral here, you will get g of e, density of states, as 1 by 2 pi I integral beta prime minus I infinity to beta prime plus I infinity e raised to beta e q of beta d beta. Okay. Here beta prime is the real part of beta, and it is assumed that it is greater than 0. Okay. Here, while taking this limits, you have to fix beta prime which is greater than 0. This, here look at this figure, this is beta prime equal to 0, the origin, and this beta prime I selected at a point which is greater than 0. Okay, now consider a line, a vertical line like this, and along this line I can say that the value is beta prime plus say iy or I beta double prime. Okay, here in the imaginary axis you have beta double prime. So you can say that the any point on this line, vertical line, is beta prime plus I beta double prime, and the lower end in the limit this length tends to infinity. The lower end can be denoted as beta prime minus I infinity, and the top end is beta prime plus I infinity. So integration is along this line. Usually, if you have to integrate in an open line, the method is close it using some contour. Okay, here it is a circle, semicircle. You close it using a semicircle, and if you can prove that the integral over this semicircle will vanish in the limit, the radius tends to infinity, then the closed contour integral will give you the value of this straight line integral, provided the contribution from this gamma, this semicircle will vanish. The limit, the radius tends to infinity. Okay, so we will calculate the density of states using this Bromwich integral in the next session for a system of ideal gas. And this modification is nothing but in terms of the imaginary part, because we are integrating in this line. So if you are writing that integral, then this becomes minus infinity to infinity. Instead of beta prime minus I infinity, becomes minus infinity to infinity e raised to this beta is beta prime plus I beta double prime into e. Q of beta is beta prime plus I beta double prime, and d beta is d beta prime, and we are fixing beta prime. In the along this line there is no variation for beta prime, so d beta prime will vanish, and I d beta double prime, this I will cancels with this I in the denominator, so you will get 1 by 2 pi. So g of e is 1 by 2 pi integral minus infinity to infinity e raised to minus beta prime plus I beta double prime e q of beta prime plus I beta double prime into d beta double prime. But we will use the technique of contour integration for calculating this, and I will explain that in the next lecture. Thank you.